This is from the handout that I gave to you today in section 3.3, and we're going to be working on the example problem number 4, which states that we have x to the third minus 12 is greater than or equal to negative 6x squared minus 5x. And we're asked to solve the inequality and write it in interval notation. So to solve the inequality, I'm going to get everything on one side and 0 on the other. So I'm going to add 6x squared to both sides and 5x to both sides. So when I do that, I end up with x to the third plus 6x squared plus 5x minus 12 is greater than or equal to 0. Now I'm going to solve this using the different properties that we used for finding real zeros of a polynomial function. The first thing I want to note is the fact that we have a polynomial of degree 3, so that means that we have 3 possible real zeros. Now the next thing I'm going to do is look at Descartes' rule of signs. And Descartes' rule of signs say I'm going to take the function, the original function, the way it's written, and see how many changes in sign I have. So I have a positive here to a positive, no change in sign, positive to a positive, no change, positive to a negative. So P of x is one variation in sign, and therefore you are going to end up with one possible or positive real zero. Then I'm going to look at P of negative x. So I'm going to put in a negative x wherever I have an x, and I'm going to raise it to the appropriate powers. And be careful when you're doing this that you make sure that you take care of all those negatives. So when I do that, I end up with negative x to the third. This becomes positive x squared, so it's plus 6x squared. And then I have a minus 5x and a minus 12. So the number of variations in sign, I have one variation here, another one here, and then there's nothing there. So I have two variations in sign. So P of x, negative x equals 2 variations. So that means that I'm going to have 2 or 0 negative real zeros. Okay, the next thing I'm going to look at is I'm going to use my rational zeros theorem. So I'm looking back at the original problem, and I'm going to take my factors of 12 and divide it by my factors of 1. So P over Q gives me my factors of 12, which are plus and minus 1, plus and minus 2, plus or minus 3, 4, 6, and 12. And they're all going to be divided by my factors of 1, which are plus and minus 1. So this just comes out to being my factors of 12, because when I divide all of these by 1, that's what I end up with. Now my next thought is, when I start to apply this, where should I look? Should I look where I have negative real zeros or positive real zeros? Well, where I have the negative real zeros, there's a chance I might have 2 of them, which is a good thing. But what if I don't have any of them? Then I would be looking for nothing. There wouldn't be anything there. So the best strategy here is to look where I'm sure I'm going to have at least one positive real zero. So I'm going to go ahead and with that, and I'm going to be just looking at my positives. I'm going to start with 1, I'll use 2, then 3, then 4, then 6, and then 12 to see if I can find as possible 0. So I'm going to use positive 1, and I'm going to go back to my equation up here for synthetic division. So I have 1, 6, 5, negative 12. Doing my synthetic division, I found a 0, which is good. So now that I found a 0, I can look at what I started off with, and what I started off with was a third degree polynomial. So that means that what I ended up with is a second degree polynomial. And that's what I'm looking for, are second degree polynomials, because second degree polynomials then can be solved by either factoring or by using the quadratic formula. So looking at this particular problem right here, it's very easily factored into x plus 3 and x plus 4. So my zeros then are x equal to 1, x equal to negative 3, x equal to negative 4. Now I need to solve the inequality. So I'm going to take these zeros and put them onto a number line and make a sign diagram. And then I'm going to split my diagram into the different intervals created by these zeros. I'm going to list all the different factors that I have. I have x plus 3, I have x plus 4, and then this one becomes x minus 1. And I'm going to look at numbers less than -4. So in the interval where it's less than -4, let's say I have -5, this would be negative, this would be negative, this would be negative. If I multiply all those together, I'm going to end up with a negative value. Picking a number between -3 and -4, I'm going to pick -3.5. This would be negative, this is positive, this is negative. Overall, I'm going to be positive in this interval. Between -3 and 1, I'm going to pick 0. So I have positive, positive, negative. We're going to be negative throughout this interval. And then to the right of positive 1, we're going to be all positive. Now looking back at this function here, the end behavior of this function, it's a third degree, so that means it's odd, and it's positive. So my end behavior means that I'm going to be going down on the left and up on the right. If I look down at my sign diagram, that's exactly what I'm going to be doing. I'm going to be going down on the left, and I'm going to be going up on the right. So if I start to draw that a little bit. And then I can go ahead and draw, and I'm going to be knowing that I'm going to be positive up here, and then I'm going to go negative down here, and then I'm going to go back up positive. So that's what my graph is going to look like. And then I want to look, where is my graph greater than or equal to 0? Where is my graph above the x-axis? Well, it's going to be above the x-axis here, and it's going to be above the x-axis here. So I'm going to write that in interval notation, and I want to know where it's greater than or equal to, so they're included, those zeros are included, so it's going to be from -4 to -3, or from 1 to infinity.